In this last video of this lecture, we will see the last group, that are the more advanced cases, in which we will uh, analyze paired proportions. That is called the McNemar's method. And we will see also equivalence test and the analysis of two-way contingency tables. Okay, so let's see this example. So we are a group who are analyzing this adolescent idiopathic scoliosis. That is when people, young people, they have this shape of the backbone, and then we want to see if there is significantly more fibrosis in one of the sides than in the other. So let's say that this is the concave side, and so we want to see if there are more fibrosis here than there, or the opposite. And about 80% of the patients need to be operated for fibrosis on one side, and on the other side only 50%. So we want to show that there is a difference between both sides. So the alternative is that one of the sides is smaller than the other. The null hypothesis is the opposite. But both measurements are coming from the same subject. So for each subject, we analyze whether he has fibrosis or she has fibrosis on one side and not on the other. So these two measurements are not independent, and these paired proportions are analyzed with the McNemar's test. So here we have a the layout of the contingency table that we will use to analyze this data. So we will have two variables. So for instance, the first group of measurements will be called X, the second one Y. So we have fibrosis on the, let's say X is concave, Y is convex. So we have no fibrosis in concave, no fibrosis in convex, no fibrosis in concave, fibrosis in convex, and so on. And then we have different proportions. So we have the proportion of people falling in this cell, the proportion of people falling in this cell. We will refer to these proportions as P00, P01, P10, P11. So what we want to show, the McNemar's test, is that P01, this P01 is smaller than P10. So the proportion of people not having fibrosis on the concave side but in the convex is smaller than people having in the concave but not in the convex. Okay, and we will use some auxiliary variables. So we will define the discordant observations. So discordant are P10 plus 01. So 00 and 11 are concordant, meaning that they don't have fibrosis on either side, or they do have fibrosis on both sides. So these are the discordant observations, and we will define this risk ratio, here, and then the number of samples that we need is this one. So we see this the confidence level term, the statistical power term, and then the effect size normalized in some special way. And we can calculate in this way, or we can also calculate in this way, where we have the P delta defined as the difference between the two P10 minus P01. And again, we see the same kind of formulas. So the confidence level, the statistical power, and the effect size, but normalized in such a way that the normalization goes up. Okay, so here are the expected values that we have. So let us see why these numbers. So we expect 80% and 50% on each side. So this if we multiply, let's say that these are so we expect 80% on the concave side, 20% on the concave side, and then we have 50 and 50, and we have to find a distribution of values such that these marginals are fulfilled. And note that this is not the multiplication of the two, so but this is what we expect. Okay, so now we can follow these design equations that these are the discordant proportions, and this delta, p delta, and the risk ratio, and one of the approximations give us 39 individuals, the second one give us 35. So we see that we need around 40 individuals to make this analysis. Okay, so let's go to a different topic that are equivalence tests. So now the equal sign goes to the alternative. This is different to the test that we normally do in biomedical science. So in biomedical science, the equal, we don't have it here, but the equal typically go to the null hypothesis. But here we are trying to show that two procedures are equivalent, not that they are different. Okay, so let's say that we are exploring a new administration route for a drug, and normally 60% of the patients respond to the drug in the normal with the normal route. How many patients do we need to study to show that the new route is equivalent to the previous one? And we want to have a statistical power of 90% if the number of responders deviate from 60% in either way. So either it is smaller than 50 or it is larger than 70. So how many do we need for that? This is the same case as what we were doing as equivalence test for the means, and the main difference is that now we have two null hypotheses and two tests to perform, and before in the standard biomedical research in the significance test, the alpha areas they are on the outside regions. So instead of being in the inside as they are here, they were in the outside, like in this drawing. But the thing with equivalence is that these roles of alpha and beta are inverted. Now alpha are in the central region, while beta are in the outside. And typically before we were talking about alpha half, now it is beta half. Okay, so yeah, there are some mistake in the slide here. This should be smaller or equal. Okay, so now we will calculate the sample size, and the sample size, again, they use this kind of binomial sums that have to be smaller than alpha and binomial sums that have to be smaller than 1 minus beta. So things are complicated, but there are approximations. So the Gaussian approximation, so P, that is the mean between the two proportions, then give us an appropriate way of normalizing. So we need 260 individuals to show that the effectivity of one of the routes is the same as the effectivity of the other route. And remind always that showing that something is equivalent normally requires many more samples than showing that something is different. And we have so this was one sample, so we were comparing this 260 was just for the new root. The other root was taken for granted that it was 60%. But what if we want to compare to the other group? So now let's say that we will have two groups, one with the old root, one with the new root, and then we again want to show that they are equivalent. And yeah, so now we will allow for a tolerance. This tolerance is this 10% that we wanted to detect and have this 90% of statistical power. But now so it has the same kind of formulas that we are having all the time, but now the way to normalize is different, and we will need 400 people. And it makes sense because before we were having 260. Now we have, with the two groups, we have 400. And the reason is that if you are comparing a group to a reference, you don't have any doubt, any uncertainty about the reference. The reference is taken for granted. However, if you are comparing two groups, now both groups have variance, and then the variance is increased, and to be sure that you have the same statistical power for the same effect size, this delta of 10% that we have fixed, then you will need a larger sample size because you have uncertainty on both groups. Okay, our last case that we will analyze is the analysis of contingency tables. So let's see what this is. So let's say that you are trying to determine whether you are studying 4 hospitals, and you know that in general the proportion of cesarean births is about a fourth of all births. So 25% should be cesareans, and the other 75% should not. So you are studying these 4, so this is what you expect, so that hospital 1, hospital 2, and so on, the proportion of cesareans is 1/4 in all of them, and the proportion of non-cesareans is 3/4. And you are studying these 4 hospitals, and you get these proportions. So you study how many births you need to study to be able to detect an increase by 10% in any one of these hospitals. So this is a problem in which we are comparing a set of proportions to a set of hypothetical proportions, to a set of reference proportions. And we have a lot of tests there. So the test that we are doing is that the alternative is that at least one of the proportions in one of the hospitals is different from the reference. So these are the proportions that we will use as reference, because we have so before this table was only considering the cesarean within each hospital. So you see that by columns these probabilities add up to 1. But if we consider the whole set of hospitals, then in each hospital we will have 1/4 of the births. So we have to multiply all these proportions by 1/4. That is what we have been doing here. And then we have this reference distribution of probabilities compared to this one, where in one of the hospitals the number of cesareans have been increased by 10%, and then the number of non-cesareans have been decreased by 10%. So we have this matrix of probabilities, and we have to compute this non-centrality parameter, so n, that is what we want to design, and then we have the sum of all hospitals and all cesarean, non-cesarean, and then we have the proportions of in the alternative minus the proportion in the reference group divided by this, and this follows a chi-squared. So the equation that we have to solve is this one, where we see we have the term related to the confidence level, the term related to the statistical power given this non-centrality parameter where n is the noun and the number of degrees of freedom is this one, number of rows minus 1, number of columns minus 1. So this is a transcendental equation where the n is very difficult to solve, at least manually, but computers can do. And this is what we will have. So we have the distribution of a statistic that is a chi-squared. When the null hypothesis is true, when the alternative is true, we will have a critical value, and from this critical value to the right, we will to the left we should have beta. From this critical value to the right we should have alpha. And in this example, n is 1,000. But 1,000 that among the 4 hospitals, so we have to observe 266 births per hospital. So this would be all cases that we have seen for proportions. In general, the take-home message would be dealing with proportions is much more difficult than dealing with means, because we have discrete distributions. So the distributions associated to these calculations are binomials, they are hypergeometric, and then dealing with these are much more difficult because we don't have integrals, we have sums. And typically we need a computer for doing the exact calculation, but we have approximate calculations that we have seen that if the assumptions of the approximation are fulfilled, then the approximation can be pretty good. And we should choose wisely the kind of design that we have. We have seen that we have many possibilities. What do you want? Do you want to construct a proportion, a confidence interval on the proportion, or the difference of proportions? Or do you want to make a test on one sample, multiple samples? And do you want to make an equivalence test? So there are many possibilities, and you have to choose your specific case. And this would be all for proportions. I'll see you in the next video.